Hello and welcome to this video about heterocyclic chemistry. Here we'll be talking about the synthesis of 5-membered heterocycles using the 1,3-dipolar cycloaddition. So a 1,3 dipole is a system in which there are 3 atoms where the charge is not equally spread out in that system. So here, for example, we can see that our number 1 has a negative charge on it, which puts a positive charge on the other end of our molecule number 3. So this will react with a dipolar file, so something like a pi system. And the 4 electrons in the 1,3 dipole will combine with the 2 electrons in the dipolar file to give a 4 plus 2 cycloaddition. We draw the arrows going from the negative charge on number 1, attacking the pi system, and then with the pi system coming round to neutralise the positive charge. These are a very useful family of reactions pioneered by Rolf Huisken, and so sometimes they're called Huisken cycloadditions. And what we're going to see is examples of 1,3 dipoles such as azides and nitrile ylides, but you may have also seen other examples such as ozone and diazoalkanes before. In terms of dipolar files, a pi system is all we need there really, so something like an alkyne, an alkene or a nitrile. So if we turn our attention towards the 1,2,3 triazoles and look at how we can synthesize this using a dipolar cycloaddition, well, we have 3 nitrogens next to each other, and that can come from an azide, so that's the species in red. And we have the 2 carbons, which would come from an alkyne. As you can see, if we draw our 1,3 dipolar cycloaddition arrows, we push the negative charge into the pi system, we use the electrons in the pi system to then go back and make a new bond, neutralizing that positive charge. And that gets us the triazole product. However, in this case, there is no real reason that the alkyne has to be the way round that it's drawn on the slide. And in fact, we could draw that the other way round and the mechanism works exactly the same. So this is one of the problems with a thermal-based 1,3 dipolar cycloaddition to make triazoles, and that's you get a mixture of different products. However, over recent years, people have developed copper catalysts to favour the 1,4 product, and ruthenium catalysts to favour the 1,5 product. And these have become some of the most useful and well-used reactions in all of chemistry. If we want to add an extra nitrogen in our ring and make a tetrazole, well, then we can use the azide again. That's going to give us 3 of the nitrogens. But now we need an extra nitrogen, so instead of an alkyne, we're going to have a nitrile. We draw the exact same mechanism, the negative charge coming in from the nitrogen, attacking the pi system in the nitrile, and then nitrile going back and neutralizing the positive charge. This time, because there's now 4 nitrogens, there is no element of symmetry or selectivity, and we see a single product that will quench with water, and we'll remember that the H on a tetrazole can tautomerize, so that H can sit on any one of the nitrogens in our ring. Now, if the 3 nitrogens are not next to each other, so in example in a 1,2,4 triazole, we can no longer use an azide to make this molecule. Instead, we can use the same nitrile as our dipolar files last time, but now instead of 3 nitrogens, we need 2 nitrogens and a carbon. And so we can get this if we take this chlorine compound and treat it with a base. This gives us a nitrile ylide, which is one of the dipoles that we saw before, and we can draw the exact same reaction arrows again, which will come round and form those new bonds that we need for the product. If we look at all these reactions a little bit more slowly, our 1,3 dipole is a system in which there is 3 atoms and the charge is not spread evenly across those. So there is more negative charge on one end and more positive charge on the other one. Then, if we have a suitable dipolar file, something like a pi system, we can draw these pericyclic arrows which go around in a circle. So we start off at the negative charge, that comes around and attacks the pi system then neutralizing the positive charge. In the case of 1, 2, 3 triazoles, our dipole will be an azide, and our dipolar file will be an alkyne. So if we just draw those exact same arrows, the negative charge coming round, attacking the pi system, and the electrons from the pi system making that new carbon-nitrogen bond and neutralizing the positive charge on the nitrogen. And this gives directly our triazole product. However, there is no reason we can't draw this the other way around. So our azide is in exactly the same position, but now our alkyne is facing the opposite direction. We'll draw the exact same arrows again, but we'll see that now, instead of the R groups being 1, 4, like at the top of the video, they're now at the 1, 5 positions. Now, if we do this reaction using heat alone, what we find is that we get a mixture of these compounds. But we can selectively choose between the outcome of this reaction. If we use a copper catalyst, that will give us 1, 4 at the top of the slides, and ruthenium will give us the 1, 5 at the bottom of the video. If instead we want to make the tetrazole product, then we can use the same azide starting material. This time we're going to have sodium azide. Well, remember that azides have a resonance form, so we can either put both of the negative charges on one end or the other end. It doesn't matter which way we draw it, but obviously it's nicer to have the negative charges apart. And by following the same arrows that we saw before, but this time with a nitrile, we can see that we can make our tetrazole product. Now the negative charge, because we used sodium azide, we can draw arrows that resonate that around the ring. So it doesn't have to be isolated on any one nitrogen. So we can draw it moving across. And because it's a 5-membered ring with an odd number of atoms, we can actually draw it on each one of the 5 nitrogen atoms. And the final step for this process would be to quench that negative charge from the sodium azide, which will give us the NH bond. So we can also look to make a 1,2,4 triazole, but now, because the nitrogen atoms are no longer next to each other, we can't use the azide. So instead, what we need is 2 nitrogens next to a carbon. And we can generate that from this chlorinated hydrazone. If we treat this with a base, then we can generate our nitrile ylide in situ. So the base will remove that acidic proton on the N, and then we'll get loss of Cl-. So overall we lose HCl. Now this is a very reactive species, which is why we have to generate this in situ. But if we treat this with an appropriate dienophile, such as our nitrile compound, then again we can push the exact same arrows round, and that will give us our 1,2,4 triazole product. What we've seen here is a reminder of what a 1,3-dipolar cycloaddition is. So 1,3-dipole is 3 atoms which have an unequal distribution of charge, and they will react with a dipolar file, so something like a pi system, to generate new bonds. We've seen 3 examples of how this can be applied to heterocycle synthesis. The reaction between an azide and an alkyne to give a triazole, between an azide and a nitrile to give a tetrazole, and between a in situ generated nitrile ylide and a nitrile group to give a 1,2,4 triazole. Thanks for watching. I'll see you next time.